So today I wanted to work on, in the mainstream, I want to work on optimizing our layout in our code map. You can see that it kind of takes a pretty long time to converge. What happens is we like take every node in our map, we put it in a random spot, and we say, here are some rules on how you should kind of like approach other nodes. So we say like, if you're in the same folder, you should kind of like go towards each other. Or I guess you should go towards the node that represents your folder. And if you are called by another function or you call another function, go towards those things as well. But if those were our only rules, we would end up with like a singular point in the center of the map, right? Or somewhere, because everybody would be always pulling towards each other. So we also have like this push rule that says like, try hand wavy not to be within a range of other nodes. And what happens is in order to do that, we've kind of made like two functions. We have like pull function, which is like, if you're really far away and I want to pull you, I'm going to like start by pulling you really aggressively if you're far away and pull you only a little bit if you're really close. So kind of like something like this, where this is like a distance and this is like pull amount, right? And then on the push side, we say, okay, we'll start by if you're like touching me, we push you like really hard. And as you get farther and farther away, we will like push you less and less and less until like a certain point where you're basically useless. We basically don't push you at all, right? And theoretically, where the nodes end up is kind of like here, right? Where like the pull strength equals the push strength. They're like, okay, I found my place. Now, what sucks here is to do this push, right now, it's n factorial. We say for every point, calculate your push with every other point, except for the points that you've already checked with, right? So like one will calculate push with 2, 3, 4, 2 will push with 3 and 4, 3 will push with 4, and then because it's like bidirectional, 2, like the other side will already have been done. And this is like slow as shit. So I wanted to experiment with different ways of fixing this. Basically, I want to set a threshold and say, okay, if you're farther than this far away, just don't consider it. Which means that we need some sort of way to do spatial lookup on the nodes. And I wanted to experiment with these things called BTrees. I honestly do not believe that this is the best answer. I believe the best answer is just making a grid, right? Where we just kind of like put things into some cells and we say like, okay, these cells will be sized appropriately so that we can like, maybe you just do the cells like this distance apart or maybe half the distance apart or something, right? But like you put the points in the cells and then it's really easy to look up which cells are close to any point, right? That makes it really easy. But when I was looking up like spatial data layout, I was like finding stuff like this, like things like trees that are related to, you do like bounding box, like tree structure thing. So like this box will contain all of the boxes below it, and then you can very quickly traverse the tree. And I suspect that this is slower, because I suspect building this thing is not very easy, and I also suspect querying this thing is much slower than querying the like dumb version. But I mean, these things exist for a reason, so I feel like maybe my intuition was wrong and I'd like to try it. So for happy hour, I realized I've never fucking written a tree structure in my goddamn life, and we should probably do at least a simple tree structure once so that we can, we have an idea of where we're going. So I thought I've wanted to look at BTrees recently as well. I think that these, like, my recollection here is that BTrees are kind of like, you have like some sorted data and you want like, you want like some balance between efficiency of insertion, deletion, and lookup, as well as iteration speed. So BTrees, if I remember correctly, they basically like do your classic, like, you go left, you go right, you go left, you go right. You make a tree of stuff. Things on the left are smaller than things on the right. But like the leaf nodes are like arrays of like n elements. And that means that like each node is like really friendly to the cache, if I remember correctly. Right? It makes it so that when you're iterating these things left to right, you're traversing way less, and you're doing way more like, these things aren't like stored randomly in memory. They're stored like sequentially, at least at some level. And so I wanted to look at those because I think it's an interesting approach. I've been thinking about this a little bit for our image editor. For if like implementing like erase of points. If I want to take like the eraser and scrub some stuff out, I was thinking that BTrees might be the right answer to the data storage to make this easy. I'm not really sure. Or maybe not BTrees, but something analogous to BTrees, where you have like chunks of data organized in order, in an order. So I wanted to look at them and see. And so they're like, it's kind of like a good warm up for the archery stuff, and also a good warm up for a future eraser implementation in our image editor. So that's what I want to do. That's what we want to do. So let's do that. Is the current thing n squared over 2 equals n squared, technically? I thought it was n factorial. I thought. I could be wrong. Because every element, the first element, let's count. First element, so you have like 1, 2, 3, 4, 5. We have the first element looks at all of these, the second element looks at all of these, the third element looks at both of these, the fourth element looks at these. So that's 1, that's 5 plus 4 plus 3 plus 2 plus 1. What's a factorial? Is that not what factorial is? Oh, this is n times. So am I stupid? Yeah, you're right. I'm a dumbass. I thought that there were pluses in here. You're right. Good note. Because this would be 5 is like, what is this? 5 plus 4, 9 plus 3, 12 plus 2, 14 plus 1, 15. So this is not n squared over 2 or n factorial. It's something else. I'm a dumbass. Okay. So, but I don't think it's n squared over 2 either. I think it's something else. N times n plus 1 over 2. That's maybe right. That sounds familiar. Sum of natural numbers. Yeah, that sounds right. Because this would be 5 plus 5 times 6 is 30 over 2 is 15. Yeah, that sounds right. Which makes this not n squared. Oh, that is n squared. That's approximately n squared. N squared plus n. Yeah, okay. Good enough. Let's focus, okay? B tree. Let's do something. Okay. Let's make a file to work with. Boom. And we just delete all this shit. Because we don't care. Alright. Yo, you got me reading up on the difference between R trees and KD trees. Oh yeah, I remember you were pointing me to KD trees a different time as well. I forgot about that. I just had to pick one, but sure. I think KD trees were similar. I think R trees use the bounding box, and KD trees use like a segmentation point, if I remember correctly. R trees are preferred for changing data. Yeah, I could see that because probably the heuristic for finding a new bounding box is easier than the heuristic for finding a new segment point. Okay. So we can build a thing. Let's, I don't know, return error. Just make sure that this thing like fucking works. All right, cool. And now we have to actually do a thing. So I guess let's read BTrees. Here. Okay. So self-balancing tree data structure maintains sorted data and allows searches, sequential access, insertions and deletions in logarithmic time. Generalizes the binary search tree, allowing for nodes with more than 2 children. Unlike other self-balancing binary trees, the B tree is well suited for storage systems that read and write relatively large blocks of data. Sure, okay. Blah, blah, blah. Okay, every node has at most m children. Every node, except for the root and the leaves, has at least m over 2 children. Okay, so kind of like you can imagine this as like vector realic type shit, right? So you have some sort maybe not, sure, but you want at least half utilization, sure. Is my total wrong too? No, okay. Do you need exact results for n factorial? If not, you could use Lanko's approximation. I don't know what you're asking. I'm not sure what you're asking. Root node has at least 2 children unless it is a leaf. The root node has, okay, sure. All leaves appear on the same level. Okay, sure. A non-leaf node with k children contains k minus 1 keys. The fuck? What the fuck does that mean? What does that mean? A non-leaf node with k children, so 3 children, has 2 keys? What are the keys? Shouldn't it have 3 keys, 1 for each child? Key for comparison? Okay. Each internal node's keys act as separation values which divide its subtrees. For example, an internal node has 3 child nodes, or subtrees. It must then have 2 keys, A1, A2. All values in the leftmost subtree will be less. Ah! I see. So he's storing, like, numbers between these things. Right. Okay, sure. Internal nodes are all nodes except for leaf nodes and the root node. It's a complex binary tree. Separates the ranges. You're assuming way more knowledge than I have right now. Those are a bunch of words. I don't know what any of them mean. Internal nodes are all nodes except for leaf nodes. Okay, sure. They're usually represented as an ordered set of elements and child pointers. Every internal node contains a maximum of u children and a minimum of l children. Thus, the number of elements is always 1 less than the number of child pointers. Blah, blah, blah. Okay, root nodes. Children has the same upper limit as its internal nodes, but has no lower limit. Sure. Informal description. That's what we like to see. That's what we like to see. We like to see informal definitions around here. Okay. So we have some sort of like bucket size, I guess. And everything has to be at least half utilized. Okay. I feel like just looking at this picture, we can like figure it out, right? This is so informal. Look at this. That's a lot of stuff, dude. Okay. Maximum potential search keys. Pointer child node, which starts a subtree. Pointer to the record, which stores the data. Blah, blah, blah. Okay. How does like insertion and deletion? To maintain predefined range of child nodes, internal nodes may be joined or split. Usually the number of keys is chosen to vary between D and 2D, where D is the minimum number of keys and D plus 1 is the minimum degree or branching factor of the tree. Okay. A factor of 2 will guarantee that the nodes can be split or combined. If an internal node has 2D keys, then adding a key will be accomplished by splitting the hypothetical thing into 2. Okay, yeah. So D here is just like, yo, if you've hit your fucking capacity, you gotta split your shit. Then after insertion into 2 sibling keys and inserting the mid value key into the parent. Depth only increases when the root is split. maintaining balance. Interesting. Interesting. Okay. Cool. That seems reasonable. I guess let's just start typing, and we'll eventually come up with something. Okay. So I guess what we have, like, node capacity, right? This is going to be like, I don't know, we'll start it at like 8. We'll say we can have 8 elements per thing. 8 elements per chunk. So we need some sort of storage format here. Also, do we know, I guess we need to decide how many children we're allowed to have. How is that decided? Is that kind of like hard coded? Or is that, I guess, like the root node gets split? So I guess number of children. No, that has to be defined somewhere. Otherwise, you could just keep splitting the root node over and over and over and over again. So how do they decide when to go down a level? Every node has at most m children. Here we go. So let's start with 3 or something. Every node except for the root and leaves has at least m over 2 children. Okay, so I guess this should be an even number. The root node has at least 2 children unless it is a leaf. And then, do nodes contain data here? Yeah, they do. So 1, 2, 5, 6, 7. Oh, interesting. 7, 9, 12, 16, 18, 21. I see. So the root node. So does that mean that these two things have to be tied together? They do, right? Node capacity and max children are like the same. Because the keys in here are the same as the split points. I see. I was imagining that you have like split points here to mark for like quick traversal, but the split points are actually like part of the data in this node. I see. So node capacity and max children are the same. No, node capacity is 1 less than the number of children. Yes. So let's just start this at like 4 or something, because that'll be easier to test. Maybe even 2 will be easier to test, but we'll see. We need some sort of like storage format. So I guess we can probably store this as a linear array, probably. And your like tree levels could probably just be like jump points into this array. I'm pretty sure that works. We'll find out later. And our node here has, it would be nice if this capacity was compile time so that we could store the nodes in line. So let's do that. Node capacity is a comp time int. Returns a type. And then we return our struct like this. Are we using Zig? Yep. Okay, so now that means that the storage is unbounded. Okay, but each node now has like split points that are node capacity amount of them. And these are going to have T, which is the type that we're working with. Okay, so we have this many of these things. Why not unsafe for us? I mean, because I don't feel like it. I mean, it's just like this is fine. Who fucking cares? Okay, and then we have our split points. And our children, I believe, will have implicit. Can they have like implicit addresses? So if we store this as like root, we know that if our node capacity is 4, we know that we have 5 children. Right? Because each of the elements in here is like a split point for whether or not the child is completely below or completely above us. So in that case, we know that the root node will take up the first 5. Then, okay, let's work with a smaller number. Node cap 3. We have two elements, 3 children each. So we're going to take the first 3 elements for the root, then the next 3 for his direct children, then each of his children has to have 3 things below him as well. So it's something like nom children. It's like depth times node capacity to the power of level, maybe? That's kind of how this is looking to me. You mean like Etzinger layout-ish? Dude, I have no fucking idea. You guys keep using words like you expect me to know them. I'm just making shit up, dude. I don't know. Okay. Yeah, so then we have like... Yeah, so this is level 1, this is level 2, this is level 3. And then we need to do some offset for index into this thing, right? So if we're in level 1, we're at node 0. So if we're at level, we'll call this depth 0, we're at node 0. Depth 1, we're at indexes 1. This is wait, the 3 here, the 3 is kind of like, so the 2 is contained in here. Okay. Yes, okay, sorry, we're back. So we have the root node, then we have R1, R2, R3, each of the children of the root node. Then we have R11, R12, R13, all the children of R1, R21, R22, R23, R31, R32, R33. Okay, there we go, yes. So index here, this is depth 0, 1, 1, 1, and then 2 everywhere else. Okay, chill. So this is depth. This is node. Okay, and then we have like child index. So this is not applicable. 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay, so it looks like we just have to find the start of each thing. So that's kind of like what we're looking for is like this, 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 and this. Yeah. Plus the child index. So that sounds right to me. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the next child starts here. like here. Yeah. Which is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13? Okay. We'll get there. We'll get there. So on depth, we must be missing. We're missing something, I feel like. Where there's kind of like expansion. There's expansion of the nodes as you get deeper. Right. So we're going to have, at level 3, we have 1. So 1 plus num children times num children. Yes. And then I assume that this is like, is that right? 1 plus num children plus num children. So if we take this one out, we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is more like the sum of from 0 to depth. No, not sum. You want to like multiply? No, sum. 1 plus num children to the power of 1 plus num children to the power of 2. Yeah. Yeah, there we go. That seems kind of right. That seems kind of right. Sure, that seems good enough for now. Your layout may waste up to like 50% memory or something. Yeah, I think that's fine though. I'm okay with that. I assume that there might be a better answer later, but this means that like indexing should be very easy, which I like. Sure. Yeah, that seems fine. So so if we do like a get here for a given node index, so we're going to look at like some like depth level and child index. And what do we say? It's like for 0 to level, we look at var ret is equal to 0, ret plus equals power I num children, we said? Yeah. Yeah. And I assume that this has some sort of like intelligent integer implementation. Oh, they just kind of like fucking slam it. All right. Fine. Maybe this is actually kind of slow. Could be. Could be, but fuck it for now. Maybe this is bad, but maybe it's not. Who knows? This feels kind of shit, but I don't know. We'll see. I wonder if there's some sort of better way to calculate this. May have a smarter, fancy math way to calculate directly. But this is fine for now. Okay. So we figured out how to store nodes. Now we just got to figure out how to put the nodes in. So this is going to be like get by child, I think we'll call this, because I assume that this won't be exposed externally. I assume. Okay, so let's say that we want to like insert. Surely this is the first thing we should do. Surely. I guess probably the first thing we actually want to do is init. So let's do that. Since we always calculate pow num children n minus 1, the iteration before we can calculate pow n children n, we could do the successive multiplications ourselves. Oh yeah, which fixes the fact that like this is like redoing them over and over again. Yeah, true. Successive moles can be done ourselves to avoid looping in math pow on each iter. True. Okay, so this is gonna be like storage is equal to array list node, initialize their allocator. And surely here, when we insert, we take in ourselves and we insert some value. Okay, cool. Eventually, we're going to have to support like arbitrary types with arbitrary less than functions. But for now, we'll just only support numeric types. And that will make this work, I assume. Okay, informal definition of an insertion. Let's see if we could guess. If we were to guess what it would be you have to like, if you're empty, you just put it in the root, right? Simple. And you probably keep adjusting the root till it fills the fuck up, right? So you hit your capacity. Then when you add your fifth thing in this scenario, how many nodes? We don't have like a node capacity passed in, but in this scenario, say you hit your fifth thing, you must have to take, you either split into 3 children like immediately, or you just add 1 child node and put all of the things that were in the root into the child. And then you put your first, the fifth element just sits at the top here. Yeah. So that's one thing. We'll read what they do in a second, but let's imagine how we would do this first. So we get like, we have 1, 4, 7, 9 in here, right? This is full. We add 5 now. And I think what happens is you would like put the 5 here. And then this becomes 1, 4, 5, 7. The 9 doesn't fit anymore. And now the new root would be 9. That's how I would do this if I were to guess. Right? Because now you have 1 child and everything is to the left here. Now it might make more sense. It depends on if you want to be more balanced immediately. If you wanted to be immediately more balanced, you might want to split these up and leave more of them in the root. You could also do like something that's like, you could do it the other way, where you do 4, 5, 7, 9 in the root and add 1 down here. That's another option. So how do they split? If an internal node has too many keys, then adding a key can be accomplished by splitting a hypothetical into 2 nodes and moving the key that would have been in the middle to the parent node. So they're saying neither of what I just said. They said, let's keep it more balanced. So they're like, we'll take 1, 4, and 7, 9 and put 5 up here. Okay, sure. And then how do you ever end up with like a non-multiple of 2, or sorry, more than 2 children? Into 2 D key siblings and inserting the mid value key into the parent. Oh, so you don't go down a layer unless you're at the root. The root has special handling probably. Yeah. So in the normal case, maybe does the root not store data? Not storing data in the root could make our implementation simpler. It could. But okay, so we'll pretend that there's like stuff up here that we don't care about, and we're at some node here, and we'll say that the current state of our node is like he just has like 5. And then we have like 1, 2, 3, 4, 6, 7, 8, 9. We try to insert 10. It doesn't fit anymore. So then we put 8 up here, and then 9, 10 go over here, and we have 3 children now. Now this is not like perfectly balanced anymore because like these guys have like too much stuff in them relative to these, but I don't know if that matters or if that's like kind of combated by something else. If an internal node has okay, so how about like how does the root node work? Root node's number of children has the same upper limit as internal nodes but has no lower limit. Sure. And then does the root node I assume it's a root. It has to be the only node. Okay. They're usually composed of an ordered set of elements, blah, blah, blah. Thus, number of elements is always 1 less than the number of child pointers. Yep. We figured that already. Okay. I guess we just start, well, so we only have like sibling split rule here. What about like child split rule? After insertion by splitting would be overfilled node of 2 D plus 1 keys into D key siblings and inserting a mid value to the parent. Depth only increases when the root is split, maintaining balance. So they're probably saying that in order for the depth to increase, you have to add a split at the top. But what I don't really understand is like, do you make your way? You must have to make your way all the way down to the bottom and like propagate back up. That's kind of my assumption here. Because otherwise you don't know which node is being split or if you need a split, right? If you have a root that's full, right? And you know, he's got some stuff in here, and you have like a child who's also full and another child here who's also full, right? Let's just kind of say that this is full. And all of these guys are half empty, right? I don't know. Like, you don't know that you need to split until you have checked if you're like filling one of these guys up. So I assume that you have to make it all the way down to the bottom and propagate splits up. And then I would also assume, and then there has to be like, I would imagine that there has to be rebalancing as well. If this guy's full and you want to add a number, like if you I was imagining that like there might be cases where you want to insert something here, but I guess you always want to insert at the root, because unless you can have multiple of the same element, but I would assume that's not true. I would assume that you can only have one of each element, because this is like supposed to be like a map of some form. At least that's how I've seen it in the past, right? When I've seen it in like Rust, these things are used as like key value stores, which means that you can only have one of a key, right? These are kind of used this way. Okay. So this is a BTree, right? I did one of these once. Yep, that's what we're going for. I mean, I don't really know because I'm only like skimming the Wikipedia, so I might end up implementing something that's not that. But we'll find out. We're hoping it's close enough. Okay, so we could just try following the rules and seeing if we get some sort of emergent behavior that says what they're saying. And their rules are literally just like, okay, to maintain, surely we have to find a leaf somewhere. They don't really say how do you like figure out which node to insert to, but maybe we should read the rest of this. Okay, K is the maximum number of potential search keys for a node in a BTrees. That's what we call node capacity. The pointer to a child node, which starts a subtree, so we're just not doing that because we don't need these pointers. Pointer to the record, which stores the data. That we do need. So this is actually kind of like key storage. So I guess we're kind of implementing a set right now. But like theoretically, we might want like, you know, some sort of like value type that's stored in here. Right? I think the node holds the value, but we'll come back to that. And then the search key at 0 base node index I. What are node indices in this case? Oh, here. Internal node structure. Sure. If ki exists in any node in BTree, then ki minus 1 exists in that node where I is greater than or equal to 1. So yeah, they're saying, I think that they're probably using the same node order that we ended up with, but we should find out. Did you try to use Ghosty? I think the question has already been asked. I haven't tried it yet. I don't really know. I don't really feel like I'm missing anything right now, but maybe I am. I don't know. It's not like I don't really feel like my terminal emulator needs to be that crazy. I don't really understand why it got so much hype, to be honest. It feels like, who fucking cares? It's a terminal emulator? Like, yeah, I'm not really sure. Okay. Each leaf node, blah, blah, blah. Root node when it is leaf node, root node when it is internal node, leaf node. Okay. Yeah, so I feel like this doesn't really describe like how to pick which node to insert into, or even like traversal. But I think that we can, take a guess where we know that the keys are split points. So let's assume this is just a result of me not being able to fucking read. But we'll assume that always inserting into leaf node. So I guess that means that first we need to implement like find insertion node or something, right? Something like this. And this is going to give us a node index, which makes me kind of feel like a node ID here will make me a little happier. So get by node ID literally is just like takes in a node ID and returns a node pointer probably. And here is just literally like self key storage items at ID value. Okay. Seems reasonable. Okay. So find in the insertion node. So we start at the root. Naming this probably is kind of nice. I guess we can do something that's like root node is node ID with value equals 0. And I guess we should always have the root available to us. And here, our node capacity, we also need to say like how much of this thing is full. Yeah. So num children here. And usize here should actually be like probably more like log 2 of node capacity or something. I don't really know how to do that, right? Like if we have like less than 255 children, then this should be a U8. So this should kind of like always be a U8, right? Like in reality, it's probably enough. Okay, cool. So this thing starts at 0, and then on initialization, we have to set the root node. So storage is this, and we're gonna put a thing in here, so this thing can error out. We say storage insert, nope, append an empty node. So this thing can just be undefined by default because it's not legal to access any of his children without this. We could maybe put a fix me in here that says like stack array type might be useful here, but we'll just kind of manage it manually for now. And then I guess we have like an air defer storage deinit like this. And this is key storage, I forgot. Okay. Oh, right, but we kind of said actually that if the value would end up inside. So maybe maybe not key storage, but just storage. We'll see. We will see. Okay, so to find the insertion node, we must start at the root. Uh-huh. Then what? We look at like for 0 to current node num children. We probably take we need to get by child here, which means that we need to keep our level here. I guess. This returns a node ID. So we'll say find node ID for child level or something. I don't know. For level child. This is kind of wrong because you kind of need to walk. You need to like walk the. You need the child index for every level of the tree. Surely. We were only looking, when we were looking at this earlier, we were saying like, when we came up with this is only for the first. This is only for the first node at each depth. But we need to know which node how far into that depth we are, I guess. Which means I'm pretty sure you need to know like the whole child path here. So I guess that's why they were saying like just keep a pointer to your children in here. But fuck that shit. Fuck that shit. Surely we can figure it out ourselves. Surely. So my gut says, as with all problems, this is an iterator problem. We love iterators around here. So let's do something that's like tree iter. And he is going to keep his current node is a node ID. Yes. Then maybe he also stashes his level, like his depth, I guess we should call it. And actually, you can probably figure this out from the node ID. Probably. And then we have something that's like go to child, right? Tree navigator. Okay. So this is like child index here, which probably, can we do like child index here is U8 or something, just so that if I decide to change the type later, it becomes easy. Yeah, so we need to like figure out, we need to figure out current depth. Which we can do by doing that like power thing. Okay. We also need to figure out current offset. And then I think that we say like hold on. Everything's so hard. Everything's so hard. So there might be a way to do everything recursively that avoids the need for that. That's true. So if we have like 0, this is the root, 1, 2, 3, this is his children, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's his children. So say we're at like 6 here, right? We want to go to the start of the next level. We want to go to the start of the next level, which surely we can figure out. We can surely figure out which level we're in. Pretty sure. Pretty sure. So we want to go to the start of the next level and offset by our offset into this level times the number of children. So then we end up like, 3, 6, 9 in here to find our child node. That sounds right. That sounds right. Fuck it, I don't know. Depth. Can we do like depth for node? Sure. And then I don't know. We'll use a U8 for now, but maybe a U size for now. I don't know. It doesn't fucking matter. Doesn't really matter. Okay. So I think it's this. I think it's this, where we this is depth 0, 0, depth 1, 1, depth 2 is 3 plus 1 is 4. Yeah, okay. I think this makes sense. This makes sense. So as I was saying before, every problem is an iterator problem. So we'll say like depth start iterator. And we'll say previous. Okay, so we have like some value. And we can kind of do this fix me at the same time. So what is this? This is like this returns a node ID. So this thing starts at 0. I guess we want like POW index here. Does that matter? It might not. So we have like the first thing we do is return 0 for the root node. So depth 0. Yes. Yes. So depth 0 is this. So we say return val. Maybe we do like ret is equal to val, return ret, and then we increment value in some way, probably. You probably want the identity for previous pattern v1. That seems likely. I was gonna get there, but I think you're right. Yeah, because 0 is kind of implicitly there already. So we say what? We have num children is definitely involved in here. And presumably we do times self.prev pow. Yes. Okay. So right, so this will be 1 times num children times num children squared times num children to the 3. So that seems pretty good. And then do we just do like self val plus equals prev pow here? So we start at val 0. He gets incremented by 1 on the first iteration. Then we increase this. Then the next time we get 1, he's incremented by 3. Then we get the next. Then this becomes 9. Then we get 4. We get 4. This gets incremented by 9, which will make him 13. And is that what we got here? Yeah, that is. Okay, that seems right. Yeah. So then when we say depth for, okay, first maybe we should like let's run some code. What if we take this thing completely out so that we can test it separately of the B tree? The node ID needs to be in here, so maybe we take the node ID out as well. Maybe all of this stuff kind of lives outside. This will get filled, maybe moved around later, but so we can do like function depth start iterator takes in num children as a comp time int. And that means that we can do return struct. Like this. Okay. And can we just like test this? So with num children of 2, I guess it's like this. We're expecting like it next. We're expecting 0 first. Yes. Then we're expecting 1. Then we're expecting 3. And then, so this is 0 plus 1 plus 2 plus 4 plus 8. Right? I think that's what we're expecting. Of course, he's just pissed about all sorts of other stuff, so we'll just comment all this out for a second. What's he pissed about now? Oh, because this thing needs to be this. This is a generic type. Incompatible types, comp time int and node ID. Yeah, that's true. Then we do have to write try on all these because it's an errorable function. Node ID does not get to work this way. Okay, so it looks like that's working. Let's just double check that if I put a little flaw in this test, he fails. Okay, so it looks like our thing is working. Let's try, you know, well, maybe we'll do 2 tests here. We'll just chuck a 3 in here just to make sure that it's not like special casing. I'm sure it's fine, but so this is plus 3, plus 9, plus 27. All right, cool. Cool. We have some proof of something working correctly. That's kind of sick. Okay, so when we were trying to do depth for node, this was going to be, we make one of these guys. And we go like, we want to do something that's like, while true, we say, what, like next depth. Oh, we could probably like extract both the next and the previous depth. This is kind of what I'm thinking. So we kind of start at the beginning and we say, while next depth is less than our ID, then we have to keep going. So I think we start with like we're like root node is the previous depth. The next depth is the next thing. But it next emits the root node. So it's kind of like this. While next depth value is less than this, we say prev depth is equal to next depth, and next depth is equal to the next thing out of the iterator. And then eventually, then we're like good to just return previous and next. Which should be helpful for child navigation. Because now we can just do, we can call like depth for node given our ID. Cool. Cool, cool, cool. I wonder. Yeah, I guess that's fine. So, do we actually need the current depth? I think we do, because we know that our prev child index is going to be our node ID minus the previous dev, I think. Right, because we're like this many offset into our current depth, into our like into this chunk of storage, and this chunk of storage is literally just like the children for that layer. Yeah. So then we look at the next depth plus this index times num children plus child index. I think that this is what we want. But like, I'm really shaky on that. Today, what are we doing? Writing a B tree, we think, from scratch is so funny. It's like, yeah, we are really just kind of making it up. We're making something that's B tree like that might be a B tree. That seems reasonable to me. So can we test this? Surely. Guys, where's the bouncing balls? The server crashed and then I just never started it back up. I'm trying to take this stuff like out of the B tree itself because I feel like it's easier for me to test it out here. Maybe this is silly, but maybe this is fine as well. Actually, I guess maybe depth for node could have stayed there for now. I want to test the tree navigation first. So this can stay here. Oh, but this is used by that. That's why. Okay. So we'll put the stuff that is used first. Boom. And what goes in here now? Num children. So that means that our tree navigator needs to take in num children as well. Comp time int. Okay. I may be making things overcomplicated for myself, but fuck it. You know, who cares? Who cares? Okay, this needs to take in this now. And then can we do like tree navigator? And I don't know. First of all, if we run this test now, is he happy? He's happy. Now let's actually do some testing in here. So we'll say, let's make a navigator with 3 children, 2 children. So we probably assume that the starting node is 0. Okay. Then we say go to child 0. And we expect the current node to be node 1. Yes. This is the other way usually. They want it this way, I think. So we expect node ID value equals 1. Or we can go 1 value. Okay. Then we go to child 0 again, and we expect, if this is root, first child, second child, third child, fourth child, or sorry, this is kind of like this. I guess we expect this to be 3, and then 7, 8, Then we need 2 for each of the above. So 7, 8, 9, 10, 11, 12, 13, 14. And so if we go here, if we go to child 1, we would expect to be at 8. And let's go one more level. So 15, 16, 17, 18. So if we go to child 1 again, we would expect to be at 18, I think. This is my current expectations. Do you plan on to try to implement deletion? I don't know. I don't know. There's not much of a plan at all. We're just writing. So this thing's mad because depth for node expects num children to be passed along. And then usize does not support field access. It's 65. Sure. I think it's more. Maybe these take node IDs out. Now he's pissed at 66 because this probably needs to be value. These do not. Okay, so that's good. Let's just make sure that if I put in something like a failure in here that he gets mad, which he does. And then maybe we'll do one more. I think it's good to test a couple values just to make sure that we didn't fuck something up megally. So I also want to try going down like the right side a little more. So let's do 3. We'll go to the first child, which would be index 2. Then we'll go to the second child, which should be 0, 1, 2, 3, and we're on 2. So we have 4, 5, 6, 7, 8, 9. We should be 9 here. 10, 11, 12. And then let's go to child 0 here. So we're at 0, 1, 2, 3, 4, 5 in. So we should be at 13 plus 5 times 3 after this. So that's 28. Let's go, baby. I've always missed type safe, type F, and Z and C. Did Zig fix that? I don't know if Zig has that. I just do it with these strong types. I do this to force compilation errors for that type of shit. Because I think I'm pretty sure that these like const assignments they propagate. Pretty sure. All right. So we can now navigate through our children, which means that find insertion node should start to make sense. Right? So here we should be able to make like a tree navigator. Right? And I guess we just keep checking that like while true, we call like self get by node ID a nav current node. And we have to check each node. If the node is the value, we do one thing. If node contains val return null or return, I guess we want to return a node plus whether or not it is already in the tree or not. Whether or not the value we queried is like whether or not we're turning something that should be inserted into or something that should not be inserted into because it already exists. So can we do something like this? And here he'll say like bool exists and the node ID. You see non-exhaustive enums used for this for type safe. It's a lot. Enum usize. Yeah, I've seen that as well. I don't really like the having to type int from enum all the time. I prefer typing like x value versus int from enum x. But maybe I'm missing the fact that like if you have enum usize, enum usize, like does this allow for like if you have like this, can you have like I guess you would have to if you would have to do enum from int to assign this thing. Right? And then does this can you do a plus b if you have this? That's what I'm not sure of. We could test this. Strong enum. Let's see. If a plus b is not equal to enum from int 7, b's need to be flagged as x's. If this is not true, return error bad. Yeah, they don't let you do the add there. So then you have to do what you said and make int from int helpers, and it's like, I don't know. Just having like a struct with a dot value seems nicer to me in that case. Because then you can just extract it with dot value. You know? But maybe I'm out to lunch. Okay. So I guess here we just say for node num children, if node what is this thing called? Node split points I is equal to val, return that this thing exists, and the node is equal to node. I guess it's a nav current node is actually it. Else if it is greater. Is there one of those like std math compare? Is there like a way for me to like get like equals less than greater than in one call instead of doing this? I don't want to type this whole thing out 3 times in a row. Std math order. Thank you. That's exactly what I wanted. Yeah, hell yeah. So switch order here. If it's equal, we do what we're doing here. And then if it's greater than, we need to go to the right. So we nav go to child, and it's I plus 1. Yeah, and if it's less than, we go to child I. Because if the split point is 0 and we're less than 0, we have to go to its left child, and its right child would be, yeah, I think that makes sense. Hold on. No, this is wrong. This is wrong. This is not how this works. Because this is doing it for every child. We need to find the first child that's bigger than us. Or the last child that's smaller than us. That's what we actually want to do. Last child bigger than us? Last child... Sorry, my brain's melting. My brain's melting. So we have some node. We have some numbers. 3, 5, 7, 9. We put in number 1. So here we want to return child 0, right? If we put in 4, we want to return child 1. And if we put in 10, we want to return child 5. So this num children thing should be num split points to be less confusing. I guess num children is more fair. Num children is more fair. So we just have to be careful here when we're navigating. We need to I guess we just start with child index 0, and we go for 0 to num children minus 1, actually. And we say if node split points I is greater than us, yes. So we do this order thing. Still, if it's equal, we return. If it's greater than, we continue. And if it's less than, we break. And then here, we just have to make sure that, I guess it's here we update the child index. Yes. And actually, this gets easier too if the child index just becomes our tracking variable. So this kind of becomes like this. Yes, okay. And then this just becomes a break. I think that makes sense. That feels like it makes sense. You need diagrams, dude? I cannot visualize a real B-tree in my own head, really? Yeah, I mean, I can't really either. We're just kind of making it out of pieces and trying to see what happens. That seems like maybe reasonable. We're going to have to construct a B-tree to test this. Which we can do, probably. We can probably make a valid B-tree by hand to test it. That's probably the play. Or we could just hope that this works and start inserting and see where it falls over. I kind of like that better. Yeah, let's do that. So we should be able to be like here. Find result is this. If find res exists, we return. Oh, wait, hold on. We need some sort of exit condition for this loop, right? If we're in a leaf node, then we have like a problem. So I think all we have to do here is do like if nav current node, this get by node ID can just return an optional. And he can say like if id value is greater than or equal to the storage length, we return null. Right? So now he can just say or else break here. And wait, don't we have to do the navigation somewhere? Nav go to child. So this is if the I think it's the other way. We want, oh no, yeah. So if val is less than this thing, oh, we go to child here. Yes, here it is. Then we stash like last valid node. I think we can do it like last valid node ID, I guess. And here we say last valid node ID is nav current node. Okay, yes. So now this should tell us if we get to a leaf node, and we should end up seeing something that doesn't exist in a leaf. We should end up seeing something that doesn't exist in a leaf. Cool. So if this thing doesn't exist, then we have to put it in. So for now, can we just do like append here? And just go like self num children plus equals 1. And split points at the old num children is equal to val. Okay, we're getting somewhere for sure. We're getting somewhere. Because this will crash if we overflow, but we can just like let that happen for now. So can we just go like get node by ID. What do we say? Find res.node. Yep. And then just do like append the value here. And then we should be able to append 4 values into the root node or however many it supports. Okay, so let's say we have like 3 children of type I32. Okay. Let's make an allocator. Okay. And then presumably we need to deinit the BTree as well. Okay, so what's heap is about? No field name deinit, because I tried try here. I probably didn't implement deinit here even, actually. So I think it's just like this. This guy's mad because I probably didn't return on init. So, and then probably everyone who's using BTree here needs to use self because it's a generic type. Okay. That shockingly compiles. Okay, so let's do like BTree insert 5, 7, 3, 9 or something, right? So I guess we should, if we insert 3 things, we expect this to work. We do need to fix their ordering probably. Why not use stood testing allocator? Because I'm in main. I'm not in a test right now. And then can we just like print out like the storage? Like this. Oops. Yeah, I mean, it's not, I mean, it does seem kind of reasonable for this to be a test, to be honest. No field get by node ID. Why not? The fuck? Get by node ID, not get node by ID. Okay. 153. Or else unreachable, I guess. Okay. Expected area unit type found void. Oh, because this can't fail. This isn't a fucking vector. 169 is pissed off because child index should be a U8, probably. Child index. I think we had a name for this. Yeah, we did. Hell yeah. Go to child is mad because things const. We probably need to return the result true. So if we get through all of this stuff, we say exists false and node is equal to last valid node ID, probably. Okay. This thing is mad because I probably have to put an ampersand here. True. All right. So this thing gets pissed off at 170 because he's saying num children is equal to 0. So I can't subtract here. Yeah, that's true. So if num children is 1, we still have... I assume if num children is 1, we have no split points, right? If the tree is like 1, like I have there are 4 slots down here. We need to decide what we do. Like it's supposed to be that if I have 2 and 4 in here, or 2 and 5 in here, then I have like 1 child that has stuff to the left of 2, 1 child that has stuff in between 2 and 5, and 1 child that has stuff greater than 5, right? That's what's supposed to happen here. And so if we have 1 child, then we can't have a split point. Because unless the split point is like things that are greater than child or less than, yeah, it'd have to be one. It would have to be 1 split point that is greater than all children. So I guess that's fair. So is a saturating sub here sane? Probably. I think I'm pretty happy with the idea that if my num children is 3, this should be while this is less than 2. That makes sense. I think saturating sub is fine there. 152 is pissed off because we ended up in a case where the thing exists, but we can't get it. Oh no, wait, I'm a dumbass. I'm a dumbass. So in what case? Yeah, I guess the node might not exist here. So if the node doesn't exist yet, we need to like expand our array until the node does exist. Child index plus 1 is less than node num children. That does seem kind of more generically correct, huh? Yeah, that does seem to solve the problem. Good eye. So let's maybe debug this thing, because now I'm struggling. I don't really know what's happening. So let's find out what's happening. So on insert, we are at like the first? We're at the first insertion. Okay. So first insertion, we get some sort of find res. He says, yo, you need to put this thing in node 1, and it does not exist. So I think that's fair. That's true, right? So if we're at the root node here, and we're trying to insert the first child here, this is value 1. So that makes sense. And it doesn't exist. So I think that what we have to do here is we need to do like get by node ID or null, I think is this one. And this is resize, like get by node ID and resize. This is a bad name, but fuck it. And then here we say what, like append a slice, resize, I guess. We should resize this to like resize to storage to like to fit whole depth level. But this is fine for now. This is fine for now. And then I think that this leaves things like in an undefined state. Yeah, so we say like old val is, or old size is self key storage items land. Then we mem set from old size to ID value. And we set all of these to an empty node. Like this. Okay, get by node ID. So this guy is now get by node ID and resize, which means that this thing can't ever return null. And then the other guy who called this is or null, because he doesn't want to resize. Okay. So he's pissed because we need to write try here, which means that this can fail, which means that this needs to write try here. Okay. Oh, right. I always forget to write items here. I always forget. Okay, so now he still crashes here, actually. Because the resize need to be +1. Okay, so now he's pissed at split points self num children equals val. Self num children seems to be undefined memory. That 170 looks a lot like the undefined memory value in Zig. Oopsies. So what's he pissed about here? Num children here is somehow invalid. which is confusing because I would think that every time we resize the key storage here, fine. I'm a fuck up. I get it, okay? I get it. I fucking get it. Okay. So that's looking promising. That at least succeeded. Looking at the storage is absolutely fucking useless. So I guess we... What? Like... Need some way to, like, render the tree? I guess. How do we want to do that? What's the simplest way? I guess some sort of like DFS. Okay. And then I guess it's probably like the tree navigator probably gets a go-to parent. Oh, it's so not trivial. There's just so much stuff. For now, let's just show the root. Can we just look at like split points from 0 to... Okay. We'll just do this. Root split points from 0 to root num children -1. And then all the children are empty by default, I guess. This idea of leaf node finding is wrong, huh? We don't actually want to check if the thing is null. We want to check if the leaf is empty. So that kind of makes me think like leaf nodes and inner nodes are different. They're different because leaf nodes have like elements in them. And inner nodes, like the index here, like depends. What this means depends on if we're like an inner or a leaf node. You know what I mean? Yeah. So we probably want to do something like this, where we start as like a leaf node. And this we'll just call it elms and num elms. Keys, maybe. Okay. So now num elms here can refer to however many elements are in the leaf node. And then what we have to do is when we want to work with number of children, which doesn't exist here. Here we have to like check. Here we get by node and resize. There's no more or null here. But we can probably assume that this thing should exist if we're only walking. Then here it's if node type is equal to leaf, this is when we break. Okay. And so now num children, this is elms now, and we're assuming here that I wonder if we do like this. No, I think this is fine. That's fine for now. Sorry, num elements. There, that feels like maybe kind of right. Okay, so we have 573 in our root node. That's good. We need to sort them, probably. Although maybe yeah, they need to be in order, so... Is there like insert? Is that allowed? Stable in place sort. Sorts in ascending order with the given. This. How can you do an insertion sort without insertion? Am I fucking stupid? I feel like I'm stupid here. I feel like I'm losing my mind. You can't how can you insertion sort without inserting? What do they do? So they take in A and B, indicating the index of an item, which takes two usize parameters indicating the index of an item. Sorts in ascending order with respect to less than. So, yeah, I don't understand. I don't understand. Fuck it. We'll just do something stupid and then come back to it. We'll just ask for do I have to make my own less than function here? Fuck. What do they fucking want in here? Fine. Fine. Okay, and this is return LHS less than RHS. Okay. Okay, sure. So now we should get the things in order. We get 357. Hell yeah. And we'll put a fix me here. Surely this is not the way. The most efficient way of sorting on insert. Like, surely. Surely. But it's good enough for now. Okay, so now let's start. Like, when we put in 9 here, he should crash. He does, because now it's out of bounds. So now we have to figure out how to break this shit up. And so what did this thing say? It said split into two children. Split into two children. And make sure that everything bigger is on the right, everything less is, yeah, split it. Take the middle, the median value of all of these guys, keep him in the root, and then, yeah, here we go. Okay, so function, it's like, we take, I guess here we'll say like, we can try this. In this case, we return false. Here we return true. Okay. So if this fails, we call like split node with node and val. Surely, right? Okay. So I guess we probably want this tree navigator. And we initialize him with current node is equal to node ID. That seems reasonable. Okay. Seems reasonable so far. Then we take the stuff at this node. So we just call like get node by ID or null or something. Maybe we even just do like, is anybody else using this? No. We just say get by node ID like this. No failure. Get by node ID. We know this node ID exists. Okay. And I guess we do like num children plus 1 elements. Right? So we say, okay, we have to split this node. We take the things in the above the node we get. Like with extra is going to be this. Okay. We're going to pull this stuff out and say sort elms. This is a type. And elms is going to be a bunch of t's. Okay. So now all of this comes into sort elms. Okay. So far so good. So now we sort all of these guys with the extra stuff. So we say like with extra is equal to mem copy node from 0 to node elms from 0 to node num children. So we get these elements and we copy them into with extra. Yes. Yes. And then with extra at num_elms is equal to value chill. Now we can sort these. And we take the middle point of these. So I'm going to assert here that there's an odd number here of things. Because I want to make sure that there is like a center element to pull from. We like take the center element. So we say that like we go to child 1 here. Oh fuck, wait. It's not children. It's not children. We split it in half and make them siblings. We're supposed to make them siblings, not children. And we add the middle point to the parent. And then if that doesn't fit, then we have to split again. Yes. Yes, there's some sort of like recursive split to happen here. So we can still do this with extra and sort thing. And we'll put like a fix me in here. It's like, surely there's a smarter way. Iterate old nodes, check. And iterate old nodes, inject val in iterator if it's in order or something. Fortunately, somebody already made an is odd package. Perfect. We'll never be able to figure that one out for ourselves. Yeah, that's fine. And I guess we'll put this all. Yeah, it's fine. It's fine. And so this assertion doesn't need to happen anymore, I don't think. Okay. So we are going to need to add a like go to parent to the tree navigator. It seems to make sense. And I guess this is like, there's probably some trick here. It's probably like, so this probably still makes sense. We still need to find our offset in this thing, do we? Yes. But we probably divide this offset by num children. Probably. And then if we did something that was like, we go back a layer here. And then we probably do something that's like parent is equal to this. So we go current node value minus prev value. So this is where we are, which child of the parent we are, which probably doesn't matter. We probably don't care which child of the parent we are. No, this is our offset. This is offset into layer of tree. Right? So this is like, if we're here, where this is like this plus this relative to this index. So yeah, we take this and we divide it by the number of children. And that should give us our offset into the parent layer. Yes. Parent child index, we'll call it. I think that makes sense. And so the current node is like parent depth value plus parent child index. Times num children. Why is there a times num children here? Isn't this wrong? I mean, it can't be wrong. I mean, this seems to be correct, but I'm missing y now. I've forgotten what's going on here. So we say, which node ID is the start of this depth level? Oh, find where I am relative to the start of the depth. Right. So this is find where I am relative to the start of the parent's depth. So we just get rid of this times here. I think this is right. I think we can just do a little bit of we can just go like this and just test the way back up. So this should just be like backwards. And then we probably need like an exit case. Let's just say that if we're at the root node and we go to parent, we just keep going to the root node. That seems kind of fair. And then here we'll say if current node is the root node, return. Nothing to do. All right. Okay, let's calm this down for a second. He's mad. Sure. Brief depth again or something. It's fine. We'll come back. What do we do wrong here? Probably this. Okay, close. 73 is pissed because depth for node requires num children. And I'll just put a fix me on here. And we're like getting too much. Getting more than we need. Okay. Okay, we'll do this. Integer overflow here. So if this is like, if we are in like the root, we're, I actually don't understand why this is failing. This means that this is 0, which I feel like it shouldn't be at any point here. Can we comment out some of these things? Okay, so that's all fine. When we get to 1, also fine. Now we try to go to the root. And that's where it fails. What's the note window in NeoVim? Is it a plugin? You mean this? I don't know what you're asking. I don't know what you're asking. If you're asking about this isn't in NeoVim. This is just like watch a shell script that's running. Oh, also, I guess there is no dinner, huh? We've like just totally flown past this shit. I guess we'll just say like how do you do this? Working. I guess we'll just make a proper to do, huh? So you can't speedrun a BTree, no dinner for you. Yeah, I guess I'm just gonna keep going. Making a BTree. writing a B tree, and we'll say, I don't know. I wanted to make an R tree. I needed to warm up. Oops. Not really a warm up. Set line break. And plan of action. I don't know. We'll figure it out. There we go. uh yeah, here we go. There we are. So why can't we go to parent here if we're at, so we're saying, hey, I'm at node 1. My depth for node 1, I would think that previous depth should be 1 here. I think that this is probably, there's probably an error condition here. This should be less than or equal to. That's kind of what I'm feeling now, looking at this. All tests pass now, which is good. So it's surprising that the tests weren't failing before that. Like, but it is what it is, I guess. Maybe we weren't ever on like the exact boundary. I don't know. Something about that's weird, but it's fine. Okay, so now we can go to parent. Now we can go to parent, which means that this split node thing should be much more doable, right? So we take the first n elements. We take the first n elements, we put them in the child. Or we keep them here. So we go to our parent here, and we probably want to figure out which child we were. So here we want to be like, current child index, which will return a child index, which I thought existed. Yeah, it does. Oh, but here he's mad because I forgot a bracket. That's why. And I think that's just like this. Yeah. So this will tell us which child we are from the parent. Once you have the B tree, just erase like a little at the bottom. Opa, R tree, you're a genius, dude. You just do a little this. Wow, that's an R now. This guy's smart. This guy's smart. Dude, that's like totally my type of joke. It's so fucking stupid. Okay. So this is like fix me duplicated with parent with go to parent, but we'll figure it out. And then let's just slap a test in here that's like nav current child index is 2 because we went to child 2 here. So let's just make sure like he's mad, so that's not right. Which is a little concerning, to be honest. Current node value minus previous depth value. Oh, it means it's likely that this math is wrong somewhere. God damn it. Can we GDB the test? Can we break on the failure? Go to parent? No. Okay, we breakpoint here. Step. Next. Okay. So what are we looking at? We're at node 9. Prev depth is 4. So what's the num children here? No symbol num children, but I think it's 3. So it goes, this is this case. 0, 1, 2, 3, 4, 5, 6. So if we're at node 9, we are, that makes sense. So the depth starts at 4. And we get 13 here. That lines up. Which means that these are fine. So this is the problem, is that this should be 0, 1, 2, 0, 1, 2. Oh no, wait, this is kind of right. This is just correct. Because this is 0, 1, 2, which means that we got 1 here, and it's actually correct and my test is wrong. Because we're going back to this child, not this one. So it's actually here. Am I high? So I'm at root, I go to child 1, which is 2 here. Then I go to child 2, which is 9. Then I ask for my current child index, and it gives me 2. And it gives me 1. Oh yeah, this is off. We're on the wrong layer. This should be mod numbered children. Haha. Haha, because with this one we were looking for relative to the parent. This one we're looking for relative to us right now. Something about this doesn't feel right anymore, to be honest. But maybe it's fine. I think it actually, like, hand wavy, it feels right. So, hand wavy, it feels right. Ooh, R trees. Well, we actually got sidetracked. We thought that we could implement a B tree as a warm-up, and now we're just only on B trees. R trees are probably not making it today. Because we suck. But also, welcome, Clonky Boy. You guys know El Clonky. We rate him all the time. We love the guy. Okay. So this needs to be tried. So goes life is just like that. Yeah, for sure. Okay, so our split node needs to what? We need to take a full chunk and we need to convert him into A, B, C, D. This is our sibling. And then our parent needs to now put a split point for the thing in between. So I guess it's actually a DE here. And we need a split point of C to be put in the parent. Chill. So we sort the elements. We go to the parent. We say insert. We need like some sort of like insert at node is how it feels. And then just kind of like the bottom half of this comes in here. Then we fix our children first here, I think. So my child index is this. We go to parent and then go to child. My child index plus 1. Now we have a problem if this is out of bounds. That would be a problem. But we'll ignore that for now. We just ignore problems and then they come up later and we fix them. So then we're like, so we take the, I guess before we do any of that, I'm kind of back into thinking that I like the idea of this being an odd number of elements. Because otherwise it's just too much for my poor little stupid brain to handle right now. So we say, okay, odd number of elements. The center one goes into the parent. The left ones go to me. The left ones go to them. So node, we have like a split point is num children over 2 plus 1, I think. So if there's like 4 children, when we have the extra element that doesn't fit, that's 5. Then we do 4 over 2 plus 1 is equal to 3. And so that's the third. Yeah, so we get 0. No, it's just this. Because now we get 0 and 1 go into 4. 3 and 4 go into the other one. Yeah, okay. So no plus 1. No plus 1. So our node elms 0 to split elm is copied from with extra 0 to split elm. Okay, that makes sense. We copy in the sorted version. And then what? Dude, every time I do this type of shit, I'm just sitting here thinking like, dude, I would flunk an interview. Like, they asked me to write a BTree on the fucking whiteboard. I'm fucking cooked, dude. I'm so cooked. Okay, so we need to like take this stuff in whatever. Node, we've copied this. Node num elms is equal to split elm. Okay. Cool. Then we navigate to our sibling through our tree navigator. And we just do something similar. We say, lucky BTrees aren't popular interview topics. Yeah, and I bet you it's probably because they just take too long. I bet you I'm being a little over the top. So this goes from 0 to split elm again, but this time we copy from split elm onwards from the extra side. Probably split elm plus 1. And then node here, we have to be careful. We need to use the sibling node here, which is get by node ID nav current node. Okay. We're chill so far. Okay, and then we go back to the parent. Okay. And we call self insert at node this thing. Right? We just insert the split elm. But like, doesn't this need to be sorted as well? Like, I guess we are pretty guaranteed that this thing will be our sibling. It has to be. I don't see a way. I could be wrong here, but I bet you like the math kind of just works out where we don't have to worry about the fact that like the sorting of our parent insertion might get like set out of order or anything. Now, obviously, we need to handle the case where this out of bounds is like really important. Like what happens whenever we get too big? But I guess we figure that out later. We'll just start here and work our way forwards, I guess. Memcopy is pissed because like this has to be an ampersand, maybe? Oh no, it's because this is var here, my bad. Expected 5 I32 found void. Hello? Oh. That's true. Sort elms needs T here. Okay. Insert at node wants ID and val. What's he pissed about here? Parent ID, not the parent. We don't need the node. Unable to resolve error set because there's some recursion here, so I'm just gonna write any error on one of these or both of them and move on with my life because I'm too lazy to handle error types properly. All right. So he's pissed because this thing needs to resize, I guess, which is pretty fair. The sibling might not exist yet. Okay, so that's not good. That's pretty fucking bad. But at least something happened. So we got 3 and 5 in the root. Then 7 and 9. Oh, because the root has no siblings. The root has no siblings. So there's probably a problem in there. So what do we do in that case? What do we do in that case? I guess we have to special case the root. Presumably, yeah, I don't really see a way around it. The root is a special case. So, I guess we just say split root. Fuck it. I don't know. And then I guess probably split root would look a little bit like split node. Okay. So to split the root, we have root node. And it's just like, probably this extra shit is the same. So fix me duped with split nodes. And what happens now? We like sort this shit with the extra thing. And then instead of going to parents here, we have to figure out like which two children are gonna get split here. I guess it's just like literally everything goes to the left and right side. Right? Right? So it's like go to child 0. Yeah, it's like we go to child 0 somewhere. Okay. So we go to child 0. Then we go to parent and go to child 1. Get the rest of the stuff in there. Okay. I guess we'll call it, this is now not sibling, this is child 2. And then here we have child 1 somehow. Uh-huh. Something like this? I don't fucking know, man. And then we literally know that we're inserting to us. Yeah. So now it's literally just like node lms 0 is equal to this. And node lms num lms equals 1. And node type here has to be inner. He's an inner node now. Yeah. Sure. So we're missing something where like our child nodes have to be flagged as inner nodes at some point as well. Probably. It feels like we can only insert children at the root, which feels kind of wrong. So I'm sure we're going to run into problems there. Okay, so that's way worse. Okay, let's insert 3 things before any splitting. 3, 5, 7. Hell yeah. So the bug is clearly when we go into insert this 9, right? It'd be interesting to see. So node does come from the root node, and at the end of this thing, we really should just have one element here. Oh, it's probably because we didn't return after split root. Yeah, that would do it. There's a 5 in there, baby. We're fucking getting somewhere. We're getting somewhere. Okay, so now we should see that the left node has... Shouldn't my assertion be failing here? Oh, but this isn't running? No, it is. Here. Shouldn't this odd check be like, Jesus Christ, we're not odd? Oh. This is supposed to be, with extra storage is this. Then with extra is a slice of with extra storage from 0 to node num lms plus 1. That's what we missed here. So now this assertion should fail because... Oops. The fuck? Oh. No ampersand, that's why. Okay, that's a little better. Now, hopefully that assertion will trigger. Which it doesn't. Non-equal lengths. Right, because that mem copy still needs to be 0 node num lms. Okay, now that assertion should get hit. Yeah, he's mad that it's not odd anymore, so let's work with a even number of elements here. Non-matching mem copy lengths at 255 now. That's kind of interesting. Why? So these are not the same length? Why not? So we're going from 0 split elem is num children over 2. So 4 over 2 is 2. 0 to split elem is 0 to 2, length of 2. With extra has a length of 5. So this should be 3 to 5 and 0 to 2, which should be the same length. So I don't really see the problem here. I mean, I'm clearly wrong, but I don't really understand why. Can we just do this? 2 and 5. Yeah. Oh, I guess maybe because this is a slice, he doesn't know. I wonder if... Yeah, it might be that. Which makes me want to go back to using the non-slice version of this thing. Oh no, he does know, because here we didn't make those fixes yet. I feel mental. Yeah, I don't know why it likes that, but okay. Okay, so we have, let's insert a 6 here. So this 6 should split this root node. And he should go 3, 5 on the left, 7, 9 on the right, 6 in the middle. So we should get a root node here with 6. Good. And if we look at, I guess we go for 0 to 3. Yeah, okay, that's really good. So we get root 6, 3, 5 on the left, 7, 9 on the right. That's really good. That's really good. So that means at the very least, the top level thing is working. So can we just start like smacking shit in here now? Like, can we just start going like, give me like 11, 12, 13, and 14. What happens now? So somebody gets mad. I would like to know where. So we're at line like 231. Okay, so we've made it past split root, and now we're trying to split like a child node. This guy's pissed because with extra len, %2 is not equal to 1. How is that possible? Num children here? Oh. Wait, so this was right before. Fuck. The B tree, I should give it, this is node capacity, so it should have been 3. And that means that everywhere else, I was a dumbass. Hold on. So let's go back to this case. So this should have fallen over on the 4th element here. Yes. So if we have 3 things. No, wait, hold on. I'm back to being confused. it's somewhere I shouldn't be using num children. With extra should just be num children, not num elements, because num children is node capacity plus 1. That's fucking confusing. Everywhere here, tree navigator should be using num children, but here we should be using node capacity fucking everywhere here. Oh, it's so confusing. That's so confusing. Okay, wait, so now we have four. So, okay, what do we expect to happen here? With node capacity of 4, this should all go first. Then we insert this. We get 5, 7 on the left, 3, 9, or sorry, 3, 5 on the left, 7, 9 on the right, 6 in the middle. Right before any of this stuff. Okay, that makes sense. Then we insert all of this stuff. So this is going to, at this point we have 6, 2, 5, 7, 3, 5, 7, 9. Now we add this stuff. This 7, 9 side gets overflowed. So this is going to become like 7, 9, 11, 12, 13, 14. That's too much, right? Which means that this is going to become, we're going to take, I guess, 6. There's going to be some, there should be 3 nodes at the top now. So this needs to get split somehow where like you could do it so that the 11 comes up. Wait, our node capacity is 4. I'm a dumbass. So this gets split here. So like, it gets split when we get to 13, I guess, which means that the 11 comes up like this, and then we get a 14 on the, I don't know where this 14 is supposed to go. Here, I guess the 12 comes up as well. Yeah, something about this doesn't feel quite right. But it could end up like this. But then we're missing like with like an empty node in the middle or something. There's something weird happening here. I wouldn't, that doesn't sound right to me. So here, we've ended up with 6, 11, 3, 5, 12, 13, 14, and we've totally lost the 9 and stuff. We've lost the 9 and 7. Right, we've pushed in 9, 7, 11 even. Oh, we have 11. So we've lost 9 and 7. Which means that I believe what happened here is we tried to push some stuff up into the parent. Right? We said, hey, 11, 12, 13. Okay, fuck, we need to draw this out again. So we're at like 3, 5, 6 at the top, 7 and 9. We add 11, he's chill. 12, he's chill. 13, he's like, oh, fuck. Too big, too big, too big. So he takes the middle point, 11, and then tries to split this into 7, 9, 12, 13. But I think what happens... Actually, let's see what happens at that point. Yeah, so we've just somehow managed to lose the 7, 9 in here. So that's going to be in like the split node segment. I don't understand how. Because we're supposed to copy the first half over here. Can we breakpoint here? Okay, so this should be on the insertion of the 13, which makes sense. So we're trying to split this stuff. Can we look at... where are we? Here. This is where we are. Trying to copy the stuff into the existing stuff into the current node. So the current node has 3, 5, 11, 12, right? Oh. Whoa, 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 whoa. Why does the current node have 3, 5, 11, 12? The fuck? Okay, so this 11 is going into the wrong spot. That's why. Well, that's at least one of the problems. So that's on like find node for insert. We're doing something fucking brain dead, I guess. We must be moving. Yeah, so I guess we want to put a breakpoint here if val equals 11. Condition 1, val value is 11. Okay. Oops, it's just val equals 11, I guess. Okay. All right. She be my tree till I split. Thanks for the contribution. Absolute fucking genius right here. Okay. Oh, it's because he thinks that it's a leaf node. Wait, it is a leaf node. So we're just a dumbass here. This exit condition feels kind of silly. I think this condition has to go down here. Instead of navigating to the next node, we just break. No, I'm missing something. So we get to the first leaf node. We go, yep, that's a leaf node. Let's get the fuck out of there. And we actually... It's the problem is that we're going to this child to begin with. We should be navigating to the other child. So we're getting a child index of 0 when we should be getting a child index of 1. Which makes me think this while condition is wrong. While child index is plus 1, so 1 is less than number of node elements, 2. Okay, let's look. Condition 1 is val equals 11. Oopsies, 11. Okay, run. Okay, so he should be at like the root node here. Okay, and so when we're at the root node, we have to look. We go through this thing. Whoa. Can we just do it again? Okay, p child index, p node num elements, 1. Aha! So this is the problem, is we need to check if we're greater or not. Which means that this has to be greater than or like this. And I feel like this child index increment only happens if we're greater. Yeah. Let's try that. So now we got 3, 5, 11 still. Not good. Condition 1, val equals 11. Okay, so we come in here. We go, what's our order here? Greater than? Less than. Whoa, okay. Oh, is it the other way around? So this thing is, yeah, this has to go the other way. We've got the condition inverted. We want to check if our value is less than, we want to keep going while the child is less than the thing, right? So if we're like, we're trying to insert 11 into, we have 3, 5, 6, 7, 9. So we take 11 and we say, is 6 less than 11? Or is 6 less than 11 is what we're looking for? Or is 11 val greater than 6? If 11 is greater than 6, we say, okay, we need to go to the next index. Yeah. Yeah. Okay, 6. So now the 11 ended up on the correct side, which is huge for us. Now the 11 is getting inserted into the greater than 6 side of the tree. Huge, 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 huge. And then he's mad at 391, which makes sense because we're just indexing too far. Okay, so now let's try adding 12 and 13 and 14. What happens now? So now we get 6 and 11. So on the left of 6, we have 3 and 5. On the left of 11, we have 7 and 9. On the right of 11, we have 12 and 13 and 14. That's correct. That's fucking correct. That's huge. That's huge. Now we need to just keep filling this tree to see what happens if we try to get to the next layer. So let's like insert, I don't know, 1, 2, 1, 2, and 4. What's that look like? So we get 1, 2 left of 3, 4, 5 left of 6, 11, 12, 13, 14 right of 11. So that makes sense so far. Okay. We could probably actually go for 0 B-tree key storage items line here. That would probably stop that thing from crashing all the time. Okay, there we go. So let's add some more. We have 6, 7, and 5. We have 8, 9, 10. I don't know. 15, 16, 17. See what happens now. That's looking pretty good too. So we have 4 elements here in the root, 5 children, 1, 2, less than 3, 4, 5, less than 6, 8, 10, less than 11, 13, 14. This is wrong. This is wrong. We should have, so 0, 1, less than 3, chill. 4, 5, less than 6, chill. 8, 10, less than 11, also chill. It's here. We should have 12, 13, less than 14 here. So there's some sort of like rebalancing order that needs to happen that we're not doing. You could write a tree to traverse the B tree. You could write a function to traverse the B tree to check if it's in order. True, we could. We could. But I kind of want to look at it. I want to look at the data right now to get a feel for what's wrong and what's not. Okay, so it would be interesting to inspect the state that got us here. So I guess the question is, like, when does it become wrong? I would assume it's when we insert this, like, 16 and 17, I assume is the problem here. No, even then it's wrong. So is it the 15? Yeah, so here is it right? 1, 2, 3, 4, 5, 6, 8, 10, 11. No, even here it's wrong. Even here it's wrong. It's the 11, 0, 1, 2, 3. Yeah. So at this point, even it's wrong. So bisect, bisect, bisect. Okay, so at this point, is it right? We have 6 and 11. 1, 3, 5 is less than 6. 7, 9 is less than 11. 12, 13, 14 is greater. Okay, that makes sense. Then we have the 2 and the 4. Still correct. Yeah. Then we have the 8. Whoa, why is that happening? 8 gets put in the wrong node. That's not what I would have expected. 7 and 9 also disappeared again? Oh, that's a really good point. Yeah, that's probably the actual problem, huh? Yeah, where did the 7 and 9 go? That's a really good point. That's a really good point. So the 7 and 9 are still here at this point. Good. So let's, okay. We have 5, 7, 3, 3, 5, 7, 9, 6. 3, 5, 7, 9, 6. 11, 12, 13, 14. They're all there. They're all there. Then we add the 1 and the 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we're still chilling. Yo, thanks for the prime. Shtabio, much appreciated. Okay, so here the 7 and 9 are gone. So it's either on the insertion of the 4 or the insertion of the 8. It's the insertion of the 4 that triggers it. So can we do print before and after here? Just to try to get a feel. Let's put an extra new line in between. Okay, fuck. We want like this. Is this part of the map project? Kind of. Kind of. Like, tangentially. Tangentially. So we figure out which, I guess we traverse the tree to figure out where we want to put this 4. And we say we want the 4 to go here into this node because this is where it belongs. It is less than 6. Then we go, okay, well, oh, I see what's happening. So we try to split this 1, 2, 3, 4, 5 into something that fits into 4. So we split it into 1, 2, and 4, and 5. Except we don't then shift these things off to the right. That's the problem. Is that when we go to our next sibling, we actually have to move all of the siblings over because this thing is getting split. Yeah. So we have 1, 2, 3, 4, 5, 7, 9, 12, 13, 14, right? And these are all like sequential in memory, kind of hand wavy. And so what happens is we take this 4, 5, we shift it over to the right, and he clobbers this 7, 9. Bad. What actually happened is all of this stuff also has to get shifted to the right, which is kind of interesting. This is like that clip from Malcolm in the Middle when selling the light bulb. Yeah, I get that a lot. I kind of like to embrace it because I think that the whole point of programming for fun is to like learn and explore and like gain tools for your tool belt, right? That you're like, oh, I've seen this type of problem before because I did it for fun. That's kind of like the point for me is that I find like exploring these problems fun, and I find like just having things to draw on like satisfying. And so just going down the rabbit hole means that like I just get more things to have in the belt. You know, and it's just like more fun. Now at work, you can't really do that because they want you to make money for them. And do like me doing this at work would be like not worth their time. And then they would get mad at me and fire me. So like I feel like the point of Fire for Fun is like if I feel like doing this, let's fucking do it. There's no cost. The cost is just that like the other thing that I'm doing for fun for shits and giggles won't get done as quick. But who fucking cares? I don't fucking care. I'm here to have fun anyways. Like what's it like? It's not about something. It's about the friends you made along the way. Right? Like it's about the programs we wrote along the way. I don't actually care about the end result of anything we're working on here. Which I know that I have friends that think like very differently. They get like really upset if they don't make like progress towards some goal over time. But I find that I just do not give a fuck about making progress. Like I just want to like I just want to like do stuff, and stuff is a big world. There's a lot of stuff. So we'll just keep going. Okay. So our problem, so we're learning things. Yeah, I guess that's kind of like the high level. Learning things. So when we split the node, what we have to do is like it's kind of like check check parent check parent for number of children. Then what? Then he's like, if there are too many children, I don't fucking know. But otherwise, shift all children to the right by one. Which should just be like a stood mem copy forwards, backwards. I think these things are backwards. So there's like an overlapping copy here. There's an overlapping copy that needs to take all of the stuff. You know, we have like contiguous storage for things at this depth. We have like this stuff. We're trying to move it to like this stuff, right? We're trying to move this into that. So it's like we can kind of like extract this information from the navigator, kind of, probably. So it's like this is we do like shift start. Okay. And if we go to the 0th child of, I think it's like this. So we go, we're like, we're here, and we want to find where the end of like the stuff in this layer is, which means it's the same as the start of the stuff in the next layer. So we go to our parent, and then down to the left 2 layers, we know where the end of this is. That sounds kind of right. Fix me. Abuse of navigator. We could just extract what we want directly. But fuck it. Okay. So we should be able to do something that's like copy my nodes in our node storage. To Hmm. So this is the shift start. Huh. This is like the full range. If there's like unfinished stuff in here, there's like empty elements in here, we need to account for that as well, which means that we need to look at like parent node is get by node ID nav current node. And we want to go to child of, I guess, parent node dot num elements. Yeah. Yeah. So this is the like existing end. There we go. Yeah. This is so fucking cooked, dude. This is so cooked. Um so we're going shift start existing end shift end. And we're trying to move it so that shift start to existing end is in the same range. So we have like shift amount is shift end minus existing end. And we go from here, we shift from we go into shift amount. Okay. From shift start. Yeah. Dude, this is so cooked. This is all so bad. But like it might work. Jesus. Fuck. It did not work. Who could have seen this coming? Index out of bounds. Index 56, length 3. Oh! Okay. I guess what we should do here is we should GDB and breakpoint here and just kind of look at what the fuck we're doing. So I don't know. What the fuck is in here? Like, what the fuck is going on here? So we're at node ID 2. We're trying to split node 2. Okay. What's our like current storage looking like? It's key storage. Our key storage has 3 things in it right now. Okay, so we're at this insert of 13. So what is our, we have 6, 3, 5, 7, 9. We've inserted 11 and 12. They end up in this node right here with the 7 and 9. And then 13 is splitting that thing, right? So we have 3 nodes right now. And we're trying to figure out how to like shift the stuff on our right over. But I guess the problem here is that there's a bunch of like unfilled nodes here. No, this shift end just has to be wrong. It's because I have to go to parent here again. Because we're fucking abusing this thing. There we go. Okay, index 6 makes way more sense. So the shift end being 6 seems reasonable. Can we just make sure this makes sense? So we have you know 0, 1, 2, 3, 4. and we're trying to shift. Maybe this doesn't make sense. Because 5 would be the start of the next layer. So if we're trying to insert into here, we should be shifting by 2. Yeah, we're trying to copy like this stuff into this stuff or something. I guess we're really just trying to copy 2 to 3. Or something. I don't really know. So shift start 3. Shift end 6. That's a problem. Surely that's not right. Shift amount 4. Correct given shift end is 6. So shift end feels like it's got the wrong value. Yeah, this feels fucking stupid. What was existing end here? Value 2. So value 2 for existing end does make sense. This is the end of the current stuff. Okay. So this is chill. What is shift start here? Surely this is wrong. Oh no, okay, shift start is 3. So we're saying like, hey, we're inserting something between 2 and 3. Like, move 3 the fuck out. Move 3 to the end over. So that's fine. It's just the shift end that's wrong. So our existing end, 2. I feel like this should be 5 if we go to parent 0, 0. So this is root 0, 0. So how is this 6? How is this 6? Okay. So here we're at 0, chill. Here at 1, chill. Here we're at 6. Not chill. Not chill. Unless I'm doing my math wrong? Four. Node capacity is 4. Which means that num children is 5. Which means that the tree navigator, I guess, should be using node capacity and not num children. Fuck off. Probably everyone here wants to be using node capacity and not num children, would be my guess. Does this get using right now? God damn it. It's so confusing that node capacity and num children are off by 1 from each other. And then surely, like, node capacity here as well. Like, surely everyone here. Which explains why these tests were working, is because I was using node capacity to calculate these, not num children, which is 1 greater than node capacity. And that's so fucking confusing. Okay. So now does this stuff look the way I expect it to? Shift end 5. Shift start 3. Shift amount 2 high. And then we also have to take into account that we only need to shift things that are valid nodes already. Jesus Christ. So I guess here, if existing node, there's something about like this existing end. If this is greater than if this is greater than something, is this greater than shift start? Yeah, and then this uses shift start, I guess. Okay. I think that makes sense. But we're really like flying by the seat of our pants. Okay, so 1, 2, 3, 4, 5, less than 6. 7, 9, less than 11. 12, 13, 14, greater than 11. So that's good. Now here, we're getting into trouble with our shift logic again. So this is in main. We're trying to insert a 4. We're trying to insert a 4. So that's literally right here, the broken spot. Sick. And here he's mad because I guess we should have looked at frame 9. Okay. So here we have shift amount. Shift start 2. Okay, so we are trying to merge, we're trying to like take the stuff on our right at node 1, node 2, and move it into node 3. So we're saying we should be taking 2 to 3 and moving it to 3 to shift end, I guess. Yeah, that's actually what we're trying to do. So we're trying to take 2 to 3, which is shift start. No. Yes. So shift amount here, is this 2? Why? Yeah, this feels wrong. We're trying to shift everything by 1, really. We can only be moving by 1. So we're looking for shift start to shift start plus 1. I think. Oh no, we're trying to shift more. We're only shifting by 1. But the amount of stuff we're shifting depends on what. So we have this much room, right? We have 1, 2, 3, blank, blank. We are trying to split 2, which means that we have to take the stuff in 3. It means, like, okay, say we had 3 and 4. That makes things easier. So we want to take this stuff and shift it into this stuff. Which means that we're trying to go to shift start plus 1 to existing end plus 1. Yeah. From shift start to existing end. Yeah. And here we just need to say, like, if existing end dot value plus 1 is greater than shift end, then we have a problem. I think that's the play. What am I doing? What am I doing? Okay, there we go. So now the 7 and 9 is no longer lost. Unfortunately, the 12, 13, and 14 are instead. Oh no! We suck! We suck, we suck, we suck! But all we have to do here is increment the parent num elms like this. And here we can say if parent node num elms is equal to max node capacity. That's on the same shit, I think. which means shift end doesn't have to exist, which means all of this stuff doesn't have to exist. Okay. We still seem to be losing this stuff, which I feel like I'm not understanding. Yeah, I don't understand. I don't understand where the 12, 13, 14 are going. This copy should take care of them. And I think parent node num elms might be taken care of for us already, so we might not have to do that. So 3, 6, and 11, this is fine. 12, 13, 14, where is this going? It means that, like, the key storage doesn't have that shit. But then why is this copy not failing? Des pointer must be greater than source pointer. Okay, that makes sense. I would like to look at this. So we are looking at this extra data, 7, 9, 11, 12, 13. Okay, let's try again. This is the only time where that's happening. Okay, so that's a good clue. Can we look at maybe... Can we look at sibling elms here? Okay, so the 12, 13 do end up somewhere. Where's the 14? Oh, the 14 hasn't been inserted yet. Because at frame 4, the 14 comes after. Okay, so we have 12, 13 going somewhere for sure. I would like to... Oh, wait, this isn't where it falls over. It's after the insertion of 4 that this falls over? Oh, yeah, okay. So I guess we run this with breakpoint here, run, and break with val equals 4. That's kind of weird. Okay. That's interesting. Definitely interesting. Interesting. By the way, there's still music playing. Not sure if it's happy hour. Yeah. I'm also unsure if it's happy hour. It is almost 4 o'clock. But this has really gotten out of hand. This has really gotten away from us. Can we break point here? And condition that val is equal to 4. Okay. So this is 3. I guess we'll just do info locals. Okay. So we are trying to shift 2, 3. So we're trying to insert a 4 here, right? We have these. This is the root. These 3 are the children. We're trying to insert a 4 here, which means that the 3, 5 should overflow into here, and the 7, 9, and the 12, 13, 14 should both get pushed to the right. Okay. So we're seeing that shift start, existing end, is in fact greater than the shift start. So that's good. We should go into here. Boom. Okay. So what can we look at the parent node num elms? 2. That means that this should pass. Am I high? He just like skipped right over this copy. I feel like. But it seems like he should have worked because node capacity here should be 4. So this copy sure should have fucking happened. Oopsies. Okay. So can we stood mem copy backwards? Oh, here we go. Weird. Okay, so the copy backwards is in fact happening. And can we look at the parameters? So we are trying to copy from 2 to 3. Fuck. I see. We've lost. Fuck. So that should be copying from 2 to 4, not 2 to 3. And it's because num elms, his meaning changes depending on if the node type is inner or leaf. Yeah. I guess. No, this is always +1. Which makes me go back to, I'm back to thinking that tree navigator should be using num children. He should be. He should be. That earlier when we were doing that, like 1, 2, 3, 4, 5, 6, 7. This is wrong because if my node capacity is, if my node capacity is 3, my num children is 4. Oh, I'm so. Yeah, so if my node capacity is 4, I have 5 children, which means that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 if I have this. Fuck! Okay, tree navigator, everywhere here, everywhere we're using node capacity, we're going back to num children, baby. I'll probably regret this again at some point, but you know. Dude, it's so confusing. It's so confusing. Tree navigator num children. Okay. I hope that's right. So now he's pissed again at this shit at main zig 271. That's here. Okay. So still in here. My life is so hard. I don't understand. I feel like this stuff is like shouldn't be that crazy. Okay. So we have with extra 1, 2, 3, 4, 5. Current node value equals 4. Okay. So we are trying to shift from 2 to 4. That makes sense now, right? Because we know that we have 7 and 9, 12, 13, 14. That's a length of 2. So that's what we're shifting. Shift start 2. Okay. Chill. Oh, is this just mad because key storage length is not long enough? Yeah, that's probably it. If self key storage items len is less than existing n value plus 1 plus 2. Okay, I think that should fix it. We're so back, baby. Look at this, look at this, look at this. 3, 6, 11, 1, 2, 4, 5, 7, 9, 12, 13, 14. That's fucking correct, dude. And that looks like this should be plus 1, actually. There we go. Oh, we're so back, baby. Okay. Let's insert all the rest of this shit and see if it's still broken. No fucking way! Look at that shit! So we have 3, 6, 11, and 14 are our root. So 1 and 2 are less than 3. 4 and 5 are less than 6. 7, 8, 9, 10 less than 11. 12, 13 less than 14. 15, 16, 17 greater than 14. That's fucking sick. Seconds to spare. I mean, we are we're actually kind of like an hour and a half over 2 hours past happy hour expectation. First try. Yeah, first try, baby. Okay. Okay. I am going to try adding some more numbers here, and I'm going to see what happens, and I'm not going to commit to fixing it because this has gotten really far away from us. But let's add 18, 19, 20, 21. Maybe even just 18, 19. Let's just see what happens. Yeah, so that does freak the fuck out, which does make sense. But it looks like, let's see what happens just before that. So 11, it looks like we get a tree that's left side 3, 6. It looks like we've lost 1, 2, 3, 4, 5. Yeah, it looks like we've lost 1, 2, 3, 4, 5. It looks like the root is like, yeah, something's just, this is just fucked. It's just fucked. So getting into level 2, totally broken. But we did manage to get through, I guess, the first layer of a BTree. So looking good, looking good. It's pretty sick that at the very least this works. Boom. So apologies for the extended confusion. But I think that it means that our idea here, that it was worth experimenting with trees at all, like doing a BTree. We were like, maybe we'll do a quick warm-up so that we can implement an R tree so that we can fix this like code map thing, right? That was if you guys remember 3.5 hours ago, that's how we introduced this. We introduced this as hold on, we get there. Viz. Okay, we introduced this as looking at this guy. It takes a long time for our code map to stabilize, right? So we're seeing like really slow movement here, and we're actually limited here by CPU right now. If we look at our like CPU usage, it's like we're at like 85% on one thread. We could go a little faster, but we couldn't go much faster than what we're doing right now. And because like each iteration of this thing is basically doing like an n squared lookup, saying, or an n squared like adjustment, saying for each node in this graph, let me push every other node by some amount because I don't want to get like too clumped up, essentially, right? So we did like a quick little profile. Here. And we were like, we look at the flame graph of this and we're like, yep, we sure are spending all of our time in calculating node pushes, which is n squared. And so we were like, what if we made an R tree here? I don't think that R tree is like necessarily the right answer, but I wanted to try it, where R tree is basically like a spatial lookup. That says like, yeah, we basically like categorize things by bounding box, and we were like, why don't we do a BTree as warm up because that would be fun, and I have other uses for that as well. And I think this is kind of saying it was worthwhile to do this warm up because we suck ass at making trees. And they might be maybe a little bit more complicated than I thought. So I'm happy to have gone down this path. But yeah, I think we'll call it there. Thanks for watching, guys. If you like what you saw, we stream most days around 12:30 Pacific time to 4 o'clock Pacific time. It is 4 o'clock Pacific time now, so if you're watching live, you should expect us to see us online from 3.5 hours ago to now. If you're watching live and you want to keep up with projects, there's a YouTube link in the Twitch description. Projects are organized into playlists. There's a GitHub link in the Twitch description. I don't know if code for this B-tree will end up on GitHub anywhere because it's kind of like scratch code, but we will see. It might end up somewhere, might not. Yeah, I think that's it. YouTube, peace out. Twitch, let's find someone to raid.